Good evening, sir.
Yeah, good evening, everyone. Am I audible to you?
Sir, good
Yes,
evening,
sir.
sir.
Yes, sir.
Audible, sir.
Good evening, sir.
Okay, good. So, good evening to all. And today we'll look at some introduction to statistics.
So, sir.
Yeah.
Normally, we will put our attendance in the chat box. Is it okay for you, sir?
Yeah, I mean, actually, I sort of at the end, I take a note of that, who have all attended. So you can mark here in the chat box, no problem.
Okay, sir. Okay. Right,
Okay.
sir. Right.
Yeah.
Right. Thank you.
Yeah. So I wanted to today talk about some introduction to statistics. Typically, we are going to look at the importance of mean of a data set and the associated standard deviation. And in that context, we'll also talk about normal distribution, which is typically used in statistical analysis. So let's take an example. Let's say we have, let's say a company is manufacturing some bearings, and we have a box that contains a lot of bearings, and you are asked to find the diameter of the bearing that the company is producing. And you are also interested to know the size variation of the diameter of this bearing. So one way to do that is to pick a sample. Of course, you cannot measure each and every bearing a company is producing. So you typically do sampling. That means a handful of bearings you would pick, and you would measure the diameter of each of these. Let's say you pick 20 of them, and you measure the diameters of each one of these 20 bearings, and you can find out the average. Typically, the mean or the average is taken as the best estimate of that particular variable, in this case, the diameter of the bearing. And in addition to the mean, you also find the standard deviation of the diameters of all these 20 bearings, the standard deviation of the data. The standard deviation typically represents the variation in the size of this bearing. So you have the mean, which is representing the best estimate of the data, and you have the standard deviation, which sort of presents the variation in the size. Now, the thing is, this average value represents the true representation of the actual data. That means take an average, whether this average value represents the actual diameter of the entire population. That means if you find the average of this 20, whether the average of this 20 represents the diameter of the bearing that a company is producing over 1 month, let's say, right? So that question still remains, because based on the measurement of a sample, fixed amount of data, we are trying to predict the behavior of a population. Okay, and the second thing is that whether the variation that we predict in this taking a sample represent the variation that we expect for the entire population, right? So in that context, we talk about some statistical tool to say that the mean actually represents the mean of the entire population. The mean of the sample actually represents the mean of the population, and the standard deviation, in fact, represents the standard deviation of the population. So we talk about the you actually, your intention is to know the true value, right? We talked about true value and error in the last class. So you basically want to know the true value of the diameter of the bearing, right? But you cannot get the true value, so you do estimation of the true value. And true value estimation is done by the mean value or the average value. Okay, let's call it X bar, right? So from estimation of the mean value, you say that my true value, which is, let's say, X prime, is X bar, that is the mean value, plus minus some uncertainty, we refer that to UX bar, and this at a P percentage. Okay, so this is actually the true value that you are trying to estimate, but actually you are estimating the mean value from the data. Okay, and this is basically the most probable estimate of the value X prime. This is the most probable estimate of true value, and this is basically the uncertainty interval. Okay, and so what does it mean? It means that we cannot really find out the true value. All we can do is estimate a true value. So we take a population, we find the mean value. We take a sample and we find the mean value, and we find the uncertainty interval, which is the standard deviation of the data in the sample, and we say that this is true. That means we have an interval here, right? X mean minus ux bar to x mean plus ux bar, right? The mean value minus the uncertainty to mean value plus the uncertainty. The probability that the true value will lie in this interval is p%. Okay. So we will be more clear about this when you talk about the normal distribution in a while from now. But if the basic framework is that, okay, so you pick a sample from anything that you want to measure, you pick a sample and you find the mean value, which is the most probable estimate of the true value. But then you have to define an interval from the standard deviation, and your true value is lying within that interval of x minus ux to x plus ux. Okay, so let's say you want to know the measurement, you want to know the temperature of a surface. So you want to, of course, know the true value of the temperature of the surface, right? But then you do measurement and you take 10 data points. You get, some variation in each data point between the data points. So you find the mean value. Then you find the standard deviation. So you have a range of temperature, right? So the true surface temperature lie within that range, okay? And the probability is p%. Okay, so we'll come to that. What is p%? So you talk about either 1 sigma, 2 sigma, 3 sigma, and so on. Depending on the probability, your this plus minus uncertainty interval will get adjusted. Okay. Now, before that, I want to talk about something called central tendency of the data, because we said that the mean value is the most probable value of the true value. Okay, so it says that if you measure temperature of a surface, right, and you want to know the true surface temperature, your data, let's say 10 data points, 20 data points you measure 10 times or 20 times, your data will be scattered, right? The data is scattered because of the random uncertainty, right? We talked about random error, and so that is if you quantify that random error, it appears in the form of random uncertainty. So even with that variation in the temperature that we get, you would observe that the data would tend to assume a preferred value or lie within some kind of interval of this preferred value, and that preferred value happens to be the mean value. That means whatever data you get, if you plot them, you will see that more data points are going to be cluttered around a fixed value, which is the mean value. So I'm going to give an example to clarify that. Let's say I did 20 measurements for any random variable. So I have I equal to 1 to 20, and I have xi. So let's say my first data is 0.98, and second is 1.07, third is 0.86. Okay, so let's say we have some variable xi. It could be anything. It could be pressure in a tube or whatever. And we take these 20 measurements, right? So you will see that it varies within a range, right? The minimum could be something like 0.68, and the maximum could be 1.34, right? All the values lie within this range. Now, if I plot this data in a horizontal bar plot, and I pick my scale, in equal interval, 0.65, 0.75, 0.85. Okay, let's say I have all these data points, and I place all these data points here in this scale. I would basically have 0.68 here, then this data here. I'm just placing these 20 data points here on the scale. Then you have, yeah, 1.34 is the highest. So you will see that this is the distribution of the data. Okay, and you see that the data is mostly cluttered around here. Okay, and if you find the mean of this data, you will see that these mean will be lying somewhere in this range. So this is known as the central tendency of the data. Okay, so this cluttering of the data around the mean value is known as the central tendency of the data. Okay, so now if we take, instead of placing these individual data on this scale, if we take intervals, okay, we say that my interval is x minus delta x less than equal to x less than x plus delta x. And I say that within this interval, the number of times these data points lie is some nj. Like, for example, if I say my x minus delta and x plus delta is 0.65 to 0.75, I have only one data point that lie within this range. So nj should be equal to 1. Similarly, if I do 0.75 to 0.85, I have only one data point. But if I do 0.85 to 0.95, I have 3 data points. So ng will be 3 if you are talking about between 0.85 to 0.95. So this way of representation of data is known as histogram, right? The same data we can present in the form of a, not just in a linear scale, but in the form of a histogram. And I can write a frequency of occurrence of data, Fj, which is called the frequency of occurrence of the data, as Nj divided by capital N, where capital N is total number of data points. Total number of data points, right? Here, total number of data points is 20. Okay, so in this particular case, in this example, your total number of data points is 20. So how do we represent this data in the form of histogram? Okay. So for histogram, there are certain rules that need to be followed. So what are the rules? The rules are that this nj, when you divide the entire input, entire data to different range, for at least one range, your nj should be greater than equal to 5 for at least one interval. Okay, and if you follow this rule, we can actually form a histogram out of this data. Let me go to the next slide. So we can say, now I put J to indicate the interval number, and I write the interval here. So the first interval, let's say I call it between 0.65 less than equal to xi less than 0.75, and my nj, and then I also write fj, that is equal to nj divided by n. So my first range is between 0.65 to 0.7. So if I go to data, I can see that between 0.65 to 0.75 only I have one value, right? Your nj equal to 1. So nj equal to 1. And now I have 20 data sets. So frequency will be 0.05. 1 by 20 is 0.05, right? Now the second, j equal to 2, I say 0.75 less than equal to xi less than equal to 0.85. This, if I see my data between 0.75 to 0.85, I have only one data. So I write nj equal to 1. So this is also 0.05. Now I go to 3. I say 0.85 less than equal to xi less than equal to 0.95. So between 0.85 to 0.95, I have
One, sir.
3 data points, right? Sorry, 0.75 to 0.85, I had the 1. 0.85 to 0.95, I have 3. Okay. 0.85 to 0.95, I have 3 data points. So I go there, 0.52, 0.85 to 0.95, I have 3 data points. So it will be 3 divided by 20 into 100, right? So 3 divided by 20 is basically 0.15. Okay. Now, similarly, I do 0.95 to 1.05. So 0.95 less than equal to xi less than equal to 1.05. So between that, I have actually 7 data points. Okay, so I can check that for you. 0.95 to 1.05, right? So you have 1, then 2, then 3, then 4, then 5, then 6, then 7, right? So you have 7 between 0.95 to 1.45. So you have 7. So that is 7 by 20. That is 0.35. Similarly, I get 1.05 less than equal to xi less than equal to 1.15. So if you look at your data, you will have 4. So 4 by 20 is, sorry, 4 by 20.
Sir, I have a question, sir.
Yeah,
When we are considering these data intervals,
yeah,
like if we say in the first interval like 0.95 less than or equal to xi less than or equal to 1.05,
yeah.
and then this one as well we are going to say 1.05 less than or equal to. So like in which interval would 1.05 belong in such a...
Okay, okay. I think that's a good question. I should have used less here, not less than equal. Okay, I did a mistake here. That's a good. Now it is clear, right?
Yes, sir.
Yeah, yeah. Sorry for that. Now number 6, that is 1.15 xi, 1.25, that is 2. So you have 0.10, and the final interval, that is 7, 1.25 less than equal to xi. It should be less than 1.35. We have only 2, so 0.10. So there are certain things that you need to check. One is that if you add all the nj's, your sum of nj 1 to so let's say they equal to 1 to some k to be equal to total number of data points, and in this case it should add up to 20, right? So 2 plus 3 is 5, 7 is 12, 16, 18, 20, right? And we can also see that sum of fj into 100 should give you 100%. Okay, so you can add all these here and multiply by 100, it should give you 100%. You can check that for yourself. So, and also we said that for at least one interval, nj should be greater than or equal to 5. So we get at least one interval where nj, this is also satisfied. Okay. Now, the question is, how do you know how many intervals to pick? Okay. How do you know how many intervals to pick? Whether I will make 7 intervals, whether I will go from 0.65 to 0.75 or 0.65 to 0.7. Why not 0.7? So this number of intervals, okay, that is the k, right? The number of intervals k is estimated as using this formula 1.85 1.87 into n minus 1 to the power 0.4 plus 1. Okay, so this is a correlation that was proposed by Bendit and Pearsall. So they had devised this correlation. So in this particular case, we can find out K. So K is basically 1.87 into n is 20, right? 20 minus 1 to the power 0.4 plus 1. And if you do the calculation, this will approximately come out to be 7. And that is the reason why we have picked only 7 intervals, not more or less. Okay, so this is from here. So when you do a histogram out of the data, you have to find out that these conditions are satisfied. Your number of intervals, and you have to also ensure that at least there should be one interval where the number of data points within at least one interval should be greater than or equal to 5. Okay. Now,
Sir,
yeah.
what happens if one of the intervals is not greater than 5?
So if you do not get the nj to be greater than 5, you can pick the number of intervals k to be less than this. That is fine. Okay. So if we, let's say you had only 2 here, what you do is now you adjust your k, right? So that this data value will be getting adjusted so that your n will be at least equal to 5. Okay, sort of in a way, this puts the maximum limit of the number of intervals that you can have.
Sir, one more question, sir.
Yeah.
How do we arrive at this number 5? Is it like pre-decided or?
Yeah. So this is something that comes from theory of statistics, that in order to use the histogram method, there should be at least one which represents number of data points that is greater than or equal to 5. Okay, I am not going to talk about the theory, but this is well established.
So just one doubt.
Yeah.
So if the number of data points should be greater than 5, then obviously the total number of data should also be greater than 5. So is
Yes.
there any limit for the total data? Or
Yeah, so
any...
you must have basically, as I said, you cannot have like 3 data points and you constitute a histogram, right, out of the data. And as we go, when we look into more into the theory of data analysis, statistical analysis, we will also see that depending on the probability with which you want to estimate your data, let's say you want to measure your temperature of a surface, and you say that I want to ensure that the data that I measure lies within the range of the measured data. The true value of the temperature of a surface lies within the range of the measured temperature within, let's say, 95%, at a probability of 95%, or at a probability of 99%, or at a probability of 90%. That probability will decide the minimum number of data points that you should have. Okay, that the minimum number of measurement that you should carry out. Okay, so typically for which is also known as confidence interval or the probability level, the typical value of n is I would say would be definitely more than 5. So typically the data set you would have 10, 20 or more than 20. Typically n less than 30 is considered a small data set, and greater than 30 is considered a large data set. So of course, if you want to constitute a histogram, then you cannot have less than 5 data points. But how many data points you want to collect, that will depend on your probability or the confidence level that with which you want to do your measurement. Okay, so that will come as part of this course as usual. Is that clear to you?
Yes, sir.
Yeah. Okay. So with this data now, we have 7 different intervals. We can construct a histogram, which we will do now. So let's say we have 0.55, 65, 75. So this so you have let's say 1, 2, 3, 4, 5, 6, 7. So you know that if you look at this table, so for each of these range interval, you have a corresponding nj. Okay, so you can put them in histogram form, which I am going to show there. So you can see that 0.95 to 1.05, you have 7, right? So your 7 is here. So you have the histogram. Which is representing like this. Then 0.85 to 0.95, you have 3. So 1, 2, 3, 4, 5, 6, 7. We have nj. So 3 is somewhere here. Right. So this is between 0.85 to 0.95. Then 0.75 to 0.5, you have only 1. So 1 is somewhere here. You have that. 0.65 to 0.75 also, you have only 1. You have it somewhere here. And 1.05 to 1.15, you have actually 4, right? So 4 is somewhere here. One 1.15 to 1.25, you have 2. So 2 is here. 1.25 to 1.35 also, you have 2. Yeah. So this is your data. Okay. Now, if you on the x-axis, you have basically the interval, right? So this is your x, I, and depending on the interval, you have the frequency of occurrence. Now, if you here basically sum of xi is basically sum of nj is basically 20, that is n. Is basically n. Now, if n tends to infinity, that means you collect a very large amount of data. Okay. You will find that this histogram eventually will turn into a curve which would look something like that. Okay. And such a curve is known as the normal distribution curve. And it also tells about the central tendency of the data. That means we see that, most of the data is going to be cluttered around somewhere in the middle where the mean value is expected to lie. So this also represents the central tendency of measured data. So any carefully conducted experimental data should sort of exhibit a central tendency. That means most of the data should fall around the mean value, okay, where the frequency of occurrence is very high. That is where most of the data should lie. Now, talking about the normal distribution curve, the normal distribution curve is indicated by an equation where the probability Px, okay, is called the probability density function. Is called the probability okay, and we can get the definition of probability density function from the histogram. So in a typical histogram, as I said, when n tends to infinity and your interval delta x tends to 0, that means your interval here becomes very small, right? And the number of data points becomes very large. Under that condition, you can define something called a probability density function as the frequency of occurrence, that is Nj, divided by n times twice of the range delta x. Delta x is basically what you see here, right? This minus that is basically delta x, okay? And Nj is here. So if you want to define the probability density function, I use the mouse. So Nj divided by n times twice of delta x under the limit when delta x becomes 0, we call that as the probability density function. Okay, probability density function. And this, for the normal distribution curve, this probability density function has a formula which is 1 over sigma square root of 2 pi into exponential minus half x minus x prime square divided by sigma square. Okay. So here you can see that your x prime is basically the true value. But since many times you do not know the true value, it is approximated as the mean value, which is x prime, x bar, which is the mean value. Okay. So if I plot this equation, which is called the normal distribution or Gaussian distribution. So this is the normal distribution. You will see that the curve looks like this. which I have already shown you from the histogram, but it basically is this. So I write the equation again. Px equal to 1 over sigma square root of 2 pi exponential minus half So this is basically your x mean. Okay. And if you want to so this is basically your px, the y-axis, and this is basically your x-axis, and this is where the true value is, or if you either true value or you approximate is as the mean value. They said here you have taken x line to be x mean. So if you want to know what is this height here, right? So you can just substitute x equal to x mean or x equal to x true. So that means the whole thing becomes 1. So this height here is basically 1 over sigma square root of 2 pi, right? When this x equal to x prime, this becomes 0. E to the power 0 is 1. So that is only 1 over sigma square root of 2 pi. And if I want to know the entire area under this curve, right? So I would write px dx integrate from minus infinity to plus infinity, then it should give me 1. Okay. And if I want to compare two normal distribution curves, like let's say in one case, my data is, sorry, I think it is not looking proper. Let me erase. Okay. Okay. So let's say for one experiment, my data looks something like this. And for another set, my data looks something like this, right? So I can say that here, this height here could be, let's say, 1 over sigma 1 square root of 2 pi. This height here is 1 over sigma 2 square root of 2 pi. I can say that sigma 2 is less than sigma 1. And the sigma, we said that is the standard deviation in the data. Standard deviation. That means if you do a measurement and you get a large sigma, that means your data points are varying a lot. Okay, your spread of the data is higher, right? And when the standard deviation is less, the spread of the data is less. That means you have more and more data concentrated around the mean value, right? So typically, if you do some measurement, you expect that your standard deviation of the data should be as small as possible, because it will enhance the central clustering of the data, the central tendency of the data. Where sigma is standard deviation, sigma square is known as variance. Okay. Variance of the data. Okay. And if you want to know what is the probability that the data will lie within a certain interval, right? Let's say this is x minus delta x, and this is plus delta x. Then you can write that probability that my data will lie between x minus delta x less than equal to x less than equal to x plus delta x. You should basically integrate from x minus delta x to x plus delta x dx dx, right? So area under the curve basically represents the probability that x will lie within the interval x minus delta x and x plus delta x. Okay, so I will stop with that. We will continue, but I think today you got an overview of when you do experimental measurement. One most important thing is that you will see if the experiments are carefully done, the central tendency of the data. Okay, that is number one. Number two is we also learned that the best estimate of the true data, that means true data value is unknown, as I said, but you want to know the best estimate of the true value, that is the mean. But then that is not enough because your data is scattered, right? Your data is all over the place. So if you want to know the true value of the temperature or pressure or whatever, you not only specify the mean, you also specify the standard deviation. Okay, that means if you, with the help of mean and standard deviation, you define a range of the value within which your true value is going to lie. That is at certain probability. Okay, so and the second other thing that we learned is that the data, the experiments, if properly conducted, the data should follow some kind of, in most cases, a normal distribution curve. That means you will have central tendency of the data, and the data should follow this Gaussian bell-shaped curve. And we will talk about how we can use the Gaussian distribution to analyze experimental data in the next class. Okay, so I'll stop here. If you have any question, we can discuss.
Sir, I have a query over here.
Yeah.
So you told that in this picture that we have drawn, where there are two curves which are showing standard deviation as sigma 1 and sigma 2.
Yeah.
So basically, sir, you told that this standard deviation should be less, right, sir?
Yeah. So when the standard deviation is small, you see that the height of the curve goes up. Okay.
Right.
That means more and more data are going to lie closer to the mean value or the true value.
Right, sir. Right.
Yeah.
So that is goodness in that way.
That is good. Yes. Yes. That is good. That I mean, I was just trying to compare these two cases, that if you do, let's say, two different kinds of measurement, and in one your sigma is less, you should prefer that data set. Yeah.
Sir, the final equation that you drew, the input that we chose with the statement probability that x will lie within this interval, that interval can be defined as the central tendency, right?
Which one? You said that this one?
Yes, sir. Yes.
Yeah. So see, here I am telling a different point. I am saying that what is the probability that the value would lie within this particular interval? So if you know this value of x, this value of x, if you integrate between the limit, the px dx, so this is basically the function, then you will get this. If you integrate from minus infinity to plus infinity, you of course get 1, because that is the total data set, isn't it? You can also find out what is the probability that my data is going to lie between x mean minus delta x and x mean plus delta x. So instead of x minus delta x, you will use the limits as x mean minus delta x to x mean plus delta x. So basically, it depends on what is the value of x, the range of value of x that you want to know. Accordingly, you can pick your integration limits and you can find the probability.
Understood. Thank you, sir.
Okay.
Sir, I'm sorry, I'm just asking one more question. I
Yeah.
probably have not got it correctly in that way.
Yeah.
This purple color curve, which is having the more sigma 2 value,
Yeah.
is a preferable one, right? So between these two data, right?
No, sigma 2 should be less. That means you would prefer the pink color curve to blue color curve, right? Sigma 2 is less means the data is more cluttered around the mean value. That means the variation is less.
Okay. Okay. I got it, sir. I got it now. Fine. Thank you, sir.
Sir, just I have one doubt.
Yeah.
So, why do we have two like definitions, one for standard deviation and one for variance? Anyway, it is the same.
Yeah. So it depends. Depending on the mathematical convenience, sometimes you use standard deviation, sometimes you use variance. So there is nothing, more than that. It is just, if you know one, you can find another. So basically, instead of sigma, they are using sigma square here. So you say that, okay, it is square of data minus mean divided by the variance. But if you take square root of that, you get, standard deviation, right? So it's just mathematical convenience. But sometimes in the analysis that you see, you will not talk about sigma square. You will only talk about sigma here. Right, you are not talking about square. So there are two names. That is the reason. If you talk about without any square, you say standard deviation. If there is a square, you say variance.
Okay, sir, got it. Thanks.
Sir, Professor.
Yeah.
Yeah. Is it possible to give the link in Google Meet, sir? Because Zoom, some of times our laptops are encrypted laptops. It was stuck in between.
Okay, yeah, we can do that. We can do that. In fact, we can do that. If you want a link to be sent to your mail IDs.
Yes, sir. Google Meet.
If you can, one of you can send me an email with all others copied. Then
Okay,
I can generate a Google Meet link, and a single Google Meet link should work, right, for some time.
Yes,
right?
Yes, sir.
So I'll create one link and send it, and we will just use it as long as it exists.
Yes, sir. Thank you very much, sir.
If anyone has Manivanan sir's email, no, there all the email IDs are accumulated.
Yeah, I will send to sir.
Yeah, one of you need to help me because I may not have that. So if you can send one of you a test mail or say that, okay, please share Google Meet link, I will send to all.
Sure, sir. I will forward to you, sir.
Yeah.
Sir, could you also please forward the syllabus in the
okay. I think somebody, one of you had asked. Let me just.
Yes, that would be me, sir. I emailed you in the morning.
Okay. Let me just hold on. Just give me a moment. I think I had the link. So, when I share the Google Meet link, if you can put a request for syllabus, I will also attach the syllabus there. I think
no problem, sir. I will do it. I will do it, sir.
Sure.
Okay. Thank you, sir.
Okay. Thank you very much. Yeah. Thanks all of you. We'll meet tomorrow.
Thank you, sir.
Thanks a lot, sir.
Thank you,
sir.
Thank you, sir.
Thank you, sir.
Thank you, Professor.